Good morning, everybody.
Good morning.
Fine. Thank you, doctor. How are you? Thank you. Thank you. I'm very happy, and I would like to thank you very much for this consideration. Thank you. Oh, okay. No problem. I am online. Thank you.
Hari, is good morning. Is my voice is clear? Okay, okay. Madam joined? Okay, okay. Madam, good morning. Okay, let's wait.
Good morning, Hari. Sir, good morning, sir. Welcome, sir.
Good morning, ma'am.
Morning. Good morning.
Good morning, all.
Yeah, good morning, madam.
Good morning, sir.
Ma'am, good morning, ma'am. Shall we start the session, ma'am?
Yes, ma. Yes, we can start.
Okay, ma'am. Honorable dignitaries, learned delegates, respected professors, and research scholars, a pleasant and fruitful morning to one and all. With the blessings of Almighty, I feel privileged to welcome you all on behalf of organizing committee of 2 days international virtual conference on computational mathematics ICCM 2K21. Albert Einstein once said, if we knew what it was we were doing, it would not be called a research, would it? It is an occasion like this we get opportunities to test our knowledge and understanding. We look forward to get an exposure about the area computational mathematics. The aim of this conference is to bring together leading academic scientists, researchers, and research scholars to share and exchange their experience and knowledge to all others in the aspects of mathematics. The motive of this conference is to discuss the most recent innovations, concepts, trends, and ideas in the field of mathematics. With this, it will be my pleasure to invite Mr. V. Ratanakumar, convener ICCM 2K21, to welcome the gathering.
Thank you, ma'am. Honorable Chief Guest, respected Principal, Management, Trustee, invited speakers, professors, researchers, and participants. A happy morning to one and all. All powers is within you. You can do anything and everything. With this positive code of Swami Vivekananda, I feel esteemed happy to welcome you all for the inaugural session of 2 days International Conference on Computational Mathematics, organized by Department of Mathematics, PPG College of Arts and Science, Coimbatore, Tamil Nadu. It's my privilege to welcome the management of PPG Group of Institution, who has provided the constant support and encouragement to organize the program. Welcome you, sir. It gives me immense pleasure to welcome our beloved principal, Dr. N. Muthumani ma'am, who always been the motivator for all us to this session. Welcome you, ma'am. I wish to express my warmest welcome to Dr. K Kangarajan Sir, Sri Ramakrishna Vidyalaya Mission Vidyalaya College of Arts and Science, who is going to share his knowledge with us. Welcome you, sir. I feel happy to offer my sincere welcome to Dr. Radha Ibrahim, Faculty of Mathematics and Statistics, Tan Thanh Tank University, Vietnam, who is the keynote speaker of this session. Welcome you, ma'am.
Thank you very much.
I would like to welcome all the invited speakers who accepted our invitation and going to spend their valuable time with us for the next 2 days. Welcome you all. It's my pleasure to welcome all the presenters and the participants from various parts of the regions who are here to attend this virtual conference. Welcome you all. I extend my welcome to all the faculty members, my fellow colleagues, and my dear students to this session. Welcome you all. I hope the conference will be beneficial and knowledgeable to you all. Once again, I welcome you all for this 2-day international virtual conference. Thank you. Have a great day ahead. Thank you, ma'am.
Thank you, sir. The greatest inspiration you can ever get is to know that you're an inspiration to others. As this quote, she is such an inspiring lady to all others. She is none other than our beloved principal, Dr. N. Muthumani ma'am. It's my honor to invite her to address the gathering.
Thank you, Deepika. Good morning, ladies and gentlemen. It's my privilege to extend to the delegates to this conference a most cordial welcome on behalf of the people of the PPG group of institutions. Seldom has a more representative international conference assembled everywhere. The presence here of delegates from so large a proportion of the various countries and the various part of our country is of itself sufficient evidence of the importance of this conference, which will attach to your deliberations. So research activities across all the engineering fields pave the way for the industrial world to strive forward with huge advancements. That too, computational mathematics involves mathematical research in area of science and engineering, where computing plays a central and essential role. Topics include, for example, developing accurate and efficient numerical methods for solving physical and biological models, analysis of numerical approximations to differential and integral equations, developing computational tools to better understand data and structure, etc. So this field is closely connected with a variety of other mathematical branches, as for oftentimes a better mathematical understanding of the problem leads to innovative numerical techniques. As an educational institution, encouragement and support to research can be provided by establishing a suitable platform for the research community to interact with each other and to share the knowledge. I strongly believe in this concept, and our ICCM 2021 aims to bring together both novice and experienced scientists with the developers to meet new colleagues, collect new ideas, and establish new cooperation between research groups. This international conference will provide a prestigious international platform by bringing together local and overseas computational researchers, faculty members, and students to exchange their experienced knowledge and expertise issues relating to computational mathematics. Sessions on different domains, keynote address from eminent professors, and the opportunity to network with the researchers will help the participants immensely in their research career. I would like to extend my sincere gratitude to our chairman, Dr. L.P. Thangavelu, and our trustee, Mr. Akshay Thangavelu, for extending their support to make this event possible. My heartfelt thanks to our chief guest, Rabha W. Ibrahim, Faculty of Mathematics and Statistics, Don Tac Thang University, Vietnam, for accepting our invitation and making this event a grand success. Thank you so much, ma'am.
Thank you very much.
We wish to welcome and thank each and every keynote speakers who have accepted our invitation and accepted to share their knowledge with the research community. We have participants from various countries and from various top institutions in our country. I welcome all participants for this conference. My heartfelt congratulations to Mr. Rathena Kumar and Dr. S. Harikrishnan for their strenuous effort to make this event possible. This proceeding of the conference has been documented with utmost care and will be published as ISBN proceedings. I believe strongly that this conference will stand as a great source of knowledge for all of you. With great pleasure and pride, I wish you all a wonderful learning and knowledge sharing and convey my best wishes for ICCM 2K21. Thank you all.
Thank you very much.
Thank you, ma'am. He always insists his fellow beings that just don't give up, try to do what you really want to do. And he set an example to the leading mathematicians in Coimbatore. With this note, let me call upon Mrs. S. Anandi, Assistant Professor, Department of Computer Science, to introduce the speaker, Dr. K Kangarajan Sir.
Thank you, ma'am. Your positive action combined with positive thinking results in success. It's my gratitude to introduce our eminent guest of the day, Dr. K Kangarajan Sir, Assistant Professor of Mathematics, Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore. About his academic qualification, Sir pursued his doctoral degree at Bharatiya University, Coimbatore. He completed his MSc MPhil at Bharatdasan University, Trichy. He done his undergraduation at University of Madras, and he has nearly 19 years of teaching experience as an assistant professor in both engineering and as well as science stream. He produced 15 MPhil and 3 PhD scholars and currently guiding 1 MPhil and 5 PhD scholars. He attended various orientation courses and refresher courses in mathematics conducted by Academic Staff College, Bharatiya University. He acted as a subject expert and a member of Board of Studies in various institutions. He is a subject expert of DC meeting conducted by Bharatiya University and PSG College of Arts and Science. He also acted as a convener of National Conference on Nonlinear Differential Equations and Dynamical Systems. Also, he is a member of Academic Council of Sri Ramakrishna Mission College of Vidyalaya College of Arts and Science. He is acting as a member of Indian Mathematical Society and the Indian Science Congress Association. He published a book chapter in differential equations and applications. He published 41 research papers in various reputed journals. He presented 5 papers in national level conferences. He is also acted as a resource person of webinar, FDP, and conference conducted by various institutions. He completed a minor research project funded by UGC. He also acted as a reviewer of focused journals of mathematics. Thank you, sir, for accepting and gracing us with your presence.
Thank you, madam, for the nice introduction. Am I audible to all of you?
Yes, sir. Yes, sir.
Yes.
Okay. It's my great pleasure and I feel very happy to be the guest of honor in the inaugural ceremony of this conference. Dr. N. Muttumani, Principal, PPG College of Arts and Science. Dr. Rabha Ibrahim, Professor, Ton Duc Thang University, Vietnam. Mr. V. Ratina Kumar, Dr. S. Hari Krishnan, conveners of this conference, organizing secretaries, invited speakers, distinguished chairpersons, and my dear participants. A warm good morning to all of you. Here, I would like to share some of the recent developments in computational mathematics. As we all know, the Fields Medal is the most prestigious award in the field of mathematics and is often described as the Nobel Prize of Mathematics. The name of the award is in honor of Canadian mathematician John Charles Fields. Fields was instrumental in establishing the award, designing the medal himself, and funding the monetary component. It is awarded to 2, 3, or 4 mathematicians under 40 years of age at the International Congress of the International Mathematical Union, a meeting that takes place every 4 years. The medal was first awarded in 1936 to Finnish mathematician Lars Alfors and American mathematician Jesse Douglas. And it has been awarded every 4 years since 1950. In 2014, the Iranian mathematician Maryam Mirzakhani became the first female field medalist. The most recent group of Fields medalists received their awards on 1st August 2018 at the opening ceremony of the IMU International Congress held in Brazil. It was awarded to the following mathematicians: Kocher Birker, UK-based Iranian Kurdish mathematician and now professor at the University of Cambridge; Alessio Figali, an Italian mathematician and now a chaired professor at ETH Zurich. Then Peter Scholz, a German mathematician and now director at the Maxi Planck Institute of Mathematics. And the fourth person, Akshay Venkatesh, is an Indian-born Australian mathematician and now a professor at the Institute of Advanced Study. The next is the Abel Prize, which is the second most prestigious international award in mathematics. The Abel Prize was established by the Norwegian government in the year 2002 on the occasion of the 200th anniversary of Niels Henrik Abel's birth. The Norwegian Academy of Science and Letters awards the Abel Prize based on a recommendation from the Abel Committee. The prize carries a cash award of 7.5 million Norwegian krone, approximately 6.55 crores of Indian rupees, and has been awarded annually since 2003. The Abel Prize for 2021 will be awarded to Laszlo Lovász of Eötvös-Loránd University in Hungary and Avi Wingerson of the Institute of Advanced Study, Princeton, USA, for their foundational contributions to theoretical computer science and discrete mathematics, and their leading role in shaping them into central fields of modern mathematics. The theory of computational complexity, which concerns itself with the speed of efficiency of algorithms, first emerged in the 1970s, and it is now established field of both mathematics and theoretical computer science. Computational complexity is now a very important field, providing the theoretical basis for internet security. Also, in the 1970s, a new generation of mathematicians realized that discrete mathematics had a new area of application in computer science. Today, algorithms and internet security applications are an integral part of everyday life for all of us. The work of Lovász and Wingerson has played an important part in this development. Lovász and Wingerson have been leading forces in this development over the last few decades. Their work interlaces in many ways, and in particular, they have both made fundamental contributions to understanding randomness in computation and in exploring the boundaries of efficient computation. Lovász's work has established connections between discrete mathematics and computer science. Born in 1948 in Budapest, Hungary, he has also served his community as a writer of books noted for their clarity and accessibility, as an inspirational lecturer, and as a leader, spending a term of president of the International Mathematical Union from 2007 to 2010. In 1970s, graph theory became one of the areas of pure mathematics able to illuminate the new field of computational complexity. One of the major impacts of Lovász's recent work is to establish ways in which discrete mathematics can address fundamental theoretical questions in computer science. Lovász has also devised powerful algorithms with wide-ranging applications. One of these, the LLL algorithm, a conceptual breakthrough in the understanding of lattices, and has had remarkable applications in areas including number theory, cryptography, and mobile computing. Currently, the only known encryption systems that can withstand an attack by a quantum computer are based on the LLL algorithm. The next person, Avi Wingerson, shared the Abel Prize 2021 along with Lovász. He is known for his ability to see connections between apparently unrelated areas. He has deepened the connections between mathematics and computer science. He was born in 1956 in Israel. His contribution to widening and deepening the field of complexity theory, which concerns itself with the speed and efficiency of algorithms. Wigderson has conducted research into every major open problem in complexity theory. In many ways, the field has evolved around him and has deepened the connections between mathematics and computer science. The most important present-day application of complexity theory is Internet cryptography. Early in his career, Wigderson made fundamental contributions in this area, including the zero-knowledge proof, which is now used in cryptocurrency technology. In 1994, Wigderson won the Rolf Nevanlina Prize for Computer Science. Among these other awards are Gödel Prize and the Knuth Prize. I feel happy to say that the theme of today's conference is much related to these recent developments, and I wish all the participants get benefited in attending this conference. I take this opportunity to appreciate the organizing committee and the advisory committee for arranging this wonderful virtual conference. I thank all of you for listening patiently.
Thank you, sir. She always been an example for the quote, "Believe you can and you are halfway there." And more than that, she became the most inspiring personality to the budding researchers in the field of mathematics. With this short note, I call upon Mrs. S. Anandi, Assistant Professor, Department of Computer Science, to introduce the keynote speaker, Dr. Rabha W. Ibrahim.
Thank you very much.
Thank you, ma'am.
Thank you. I would like to thank all of the professors and researchers in this amazing group, and to give me this opportunity to join your successful conference. I wish to all succeed in this.
Madam, Rabha ma'am.
Yes.
1 minute, we will introduce you to the participants.
Okay.
1 minute.
Okay.
Okay, thank you, ma'am. You were designed for accomplishment, engineered for success, and endowed with the seeds of greatness. It's my honor to introduce our delightful guest today, Dr. Rabha Ibrahim, ma'am, Faculty of Mathematics and Statistics, Tan Duc Dang University, Vietnam. Ma'am is one among the world's top 2% scientists listed by Stanford University in 2020. She is a member in IEEE and other Scopus journals. About her academic qualification, ma'am pursued her doctoral degree in complex systems at Center of Modeling and Data Sciences, University of Kebangsaan, Malaysia. She done her postdoctoral in Cloud Computing Center, University of Malaya. About her specialization, ma'am is specialized in area of complex systems, mathematical modeling, and applied mathematics and pure mathematics. About ma'am's career path, ma'am acted in various roles in her career as lecturer, associate professor, and also a senior researcher across different countries such as Malaysia, Oman, and Vietnam. She completed 2 funding research projects granted by University of Malaya and 1 COVID-19 related project funded by University Ajman. She is a reviewer of various Scopus journals by mathematics and also physics. She supervised and produced 8 PhD scholars, and she published 10 book chapters and 67 research papers in various Scopus journals. She presented 12 papers in international level conferences. Thank you so much, ma'am, for being with us today and gracing the occasion.
Thank you very much again. I'm glad to be here, and I am very happy to join this amazing conference. And I wish succeed to all of professors and researchers in this group. So, may I introduce my presentation for you, or later?
Hari, what's your plan, Hari?
Okay. I want to share my presentation. Can you see this presentation?
No, ma'am, it's not visible.
Okay. Okay, now is it clear?
Yes, ma'am, it is visible.
Okay, thank you very much. My presentation is about geometric function formulated by differential operators. And this field contains some definition, differential operator, and complex conformable differential operators, some example and recent applications. Geometric function theory is a branch of complex analysis, and this branch deals with the properties of analytic function, and the fundamental result in this theory is the Riemann mapping theorem. Of course, this theorem has many applications in computing, in computer science, and in general in computing, biological computing, and chemistry computing. Of course, there is some classes of analytic function. Not all analytic functions are available to recognize its geometric. This class is called the univalent function. Univalent in complex, we call any one-to-one function, we call it univalent function. So it is injective function. We focus from the class of analytic function on only the function which are injective. The main problem in this field is to describe the univalent class geometrically. The problem is asked how we can create these behaviors of these classes. Of course, there are different approaches can be considered for this generalization or creation, or maybe establish these classes. One of these method is by using differential operator. Maybe one asks, can we use linear operator, integral operator, or hybrid operators? The answer, yes, we can, but I focus in this presentation only on the differential operators. The class that we deal with, it should be like this: expansion, Taylor expansion started from Z plus summation an zn. Otherwise, we cannot do any geometric study for analytic function. It should be start directly from Z plus summation, and the summation start from n. Now, if we already have this function, what is the geometric of this function? There are two important classes of geometric presentation. The first one is a star-like. What is a star-like for this f of z? The star-likeness comes from the real of zf prime divided by f greater than 0. It is real part. The real part should satisfy greater than 0. And z should be in the unit disk. The second one is the convexity. The convexity comes from from this inequality. It should be 1 plus real zf double prime divided by f prime greater than 0. So we have star-likeness and convexity. The question now, is there another geometric studies? Of course, there is a spiral, there is mixed between them, there is concave, but the major study depends on the star-likeness and convexity. Now we proceed. For examples, the important example in this direction about univalent function, which is a star-like and convex, is the Kubi function. Kubi function simply takes this construction z divided by 1 minus z power sigma, where sigma is any natural number. When sigma is equal to 1, we have convex. If sigma is equal to 2, we have a star-like. So these are the major examples because they are extreme of star-likeness and convex function. So every convex function in the unit disk should be dominated by Kubi function of order 1, and for star-likeness, every star-like function should be dominated by Kubi function of the second type. Also, there is another Kubi function in the open unit disk, which is called rotated because of this parameter. This make it maybe for spiral geometry, but we haven't too much studies about the rotated Kubi function. Now there is a question, how to create classes of univalent functions in the open unit disk. This is the this is the major question for all researchers in geometric function theory. One of these method is by using differential operators. Differential operators appeared in geometric function theory earlier of 1981 by Salagin, when he formulated his operator simply by zf prime and the integral f of t divided by t. So it is very simple operator, but it is very active in geometric function theory. So it is just zf prime. Remember f should be univalent, started from z plus summation. Then this operator, differential operator, by using the fractional integral Riemann-Liouville operator in a complex domain, OA in 1974 present the complex of Riemann-Liouville in the geometric function. Then in 2011, these two fractional operators are considered for two parameters by Ibrahim, for two parameters. By employing fractional calculus, specifically the differential fractional operator and the two-dimensional parameters of the differential fractional differential operators, Selagian operator is converted to a fractional Selagian differential operator simply by using this construction. That was in 2009 for Samar and Owa, and this is in 2011 by Ibrahim. Then this operator, I mean Selagian operator, remember you, it is Z f prime, just Z multiplied by f prime. In 2015, Anderson and Allness presented their conformable operator. It is differential operator, and they borrowed the formula from the control theory. The operator is defined for a real number, on a real variable. X should be here a real number. But the construction of this operator does not effective in the geometric function theory. We must change this little change to extend this conformable operator into unit disk. So Ibrahim and Janjiri in 2019 made this little change in the Anderson-Allness operator to present or to formulate this conformable operator. This conformable operator contains the Selagian operator. So it is a generalization of Selagian operator. Look at here, the second term contains Selagian operator multiplied by this connection fraction. And this connection fraction, when this is equal to 0, we return directly to Selagian. So this is a generalization of Selagian differential operator, and we call it conformable Selagian operator. We need this changing here. It is little different from Anderson-Allness. Why? Because we need it in the univalent class, started from Z and then AN, ZN. This is very major construction of univalent function. Otherwise, we cannot study the geometric behavior of the operator. Then, for example, I wish to, in this example, to see the behavior of the Kubi function. Remember, Kubi function is the extreme function of convexity and the star-likeness. We see that here for the first class, or for the Kubi function of the first class, here there is the real part of Kubi function, and here there is imaginary part of Kubi function, Z divided by 1 minus Z. Under Selagian, we have this real and imaginary. So the function change its behavior geometrically here from this form to this form. But under our conformable differential operator, we have very nice symmetric geometric geometric construction. This is the real and this is the imaginary. If we see that there is a clause between the real and the imaginary, just shifted for 45 degrees. So sometimes the function satisfies more geometric, nice geometric presentation when we applied some of the differential operator. Similarly, for the second type, this is the second type for Kubi function. Under Salagine, we have this real and this imaginary, but again, under our conformable, we have the symmetric construction of Kubi function of the second kind. Kubi function of the second kind is about star-like. Look at it, is very nice. Very nice symmetric conversation here. We take alpha is equal to half and kappa 0, kappa 1. The connection is also a function here, functional connection. Maybe one asks about how we can create a problem or solve some problem or establish some problems in geometric function theory. It is maybe these are the steps to find or to consider some new study. First of all, check the ordinary differential operator, ordinary integral operator, ordinary linear operators. Then by using some kind of fractional, nowadays there are many fractional operators in real. We can sometimes we can extend it to complex. So by using any kind of fractional differential operator or integral, we can extend the ordinary into this. Then by using the reset of the fractional operators in new classes of analytic function, and then consider univalent function, and then study these functions or univalent function in a view of geometric function theory. As application, the basic application field of differential operators, complex differential operators, is in algebraic differential equation. Algebraic differential equation for complex variable is very familiar field, and it is unsolved until now. In general, it is unsolved, solved partially by using second order, third order, fourth order, and so on. Then, by generalize these classes, we can, of course, when you consider algebraic differential equation, you must find its solution. The solution is analytic. Then, by using these classes of univalent, you can find the univalent solution. Univalent solution is very important in algebraic differential equations. And then you can consider the geometric behavior of the solution. So this is the structure of using differential operators. And for example, we have in physics, there is a class of differential equation which is called the period bucket, which is very familiar in the optics and mechanics and quantum mechanics or even in wave analysis. This equation is familiar for for the researcher in this field. Simply the construction of this differential equation, I mean period pocket, it is very simple. F of z is equal to z f prime divided by f. Remember you, z f prime is the Salagine derivative. It is the Salagine derivative. So by using any kind of fractional calculus or by using conformable calculus, one can change this derivative into modify or fractional or conformable, and we have some papers in this direction. We have a fractional calculus differential operator. So after that, we consider a fractional variable bucket differential equation, and by using conformable, we have conformable Barrett bucket differential equation. This is in physics. In mathematical biology, Ibrahim 2020 modeled the turtle shell. Turtle shell is very applicable field in mathematical modeling and computational modeling. I requested to find this structure of turtle shell. I need to change some of or consider some of differential operator. In this case, I formulate a symmetric differential operator Z phi prime, but for the negative of Z. Remember you, our function, it should be like Z plus summation. This is very important to discuss the geometric behavior of the solution. By using the symmetric differential operator, we study the behavior or the shape of the turtle. There are three models of this shell, of the turtle shell. It has been published by Domosco and Varconi in 2007, and by using the equilibrium model. So the first shell, 2 equilibrium points, the second shell, 4 equilibrium points, and the third one, 6 equilibrium points. By using the symmetric differential, and by using the Kubi function, we find the same result. So this is confirmed by using the same result, but these are represent to the roots of the symmetric differential operator. So we have here 2 roots, then 4 roots corresponding to this, and then we have 6 roots corresponding to this shell. This is one of our application in mathematical biology. Maybe there is a question here. Is there another class, or there is another geometric class different from univalent class that start by just Z? And we find that there is a meromorphic multivalent function, which is different from the univalent. Univalent here, it should be equal to, the power here equal to 1. But for the meromorphically, it is minus rho. Rho maybe take natural numbers, any natural numbers. And then by using this class, we define another conformable differential operator, and this, by using this meromorphic function, we proved that the concept of differential operator is also meromorphic. So under this, we have another differential operator, which is meromorphically defined in the puncture open unit disk. We extract here the origin. The origin is not available in this construction. This is done by Ibrahim et al. In 2021. So it is very recently. These are the function of definition of our differential operator. Also, by using a quantum calculus, simply a quantum calculus is defined by this difference operator for a number q between 0 and 1. The operator is defined like this. It is the difference between the function divided by the difference between the x using q. So this is very famous in quantum physics, and recently this calculus is used too much in geometric function theory. The amazing example of this calculus is that the quantum of x power n is equal to the derivative, the quantum derivative x minus 1, and this quantum number is equal to q power n minus 1 divided by q minus 1. Maybe this calculus is little complicated for who has not interesting in fractional calculus, but for the who is very interesting in the fractional calculus, this is very familiar. This number is very interesting and very active to use it to define a new quantum differential operator. This operator is done by Ibrahim and Dmitry in 2021. Look at this number. This is the quantum number. And this quantum number make this differential operator, call it Q differential operator. Remember you that Q should be between 0 and 1, does not equal to 0, does not equal to 1. So any number between 0 and 1. So as a conclusion, in geometric function theory, of course, there are many computation and many application in computational fields like physics, biology, and quantum physics. We based on some differential operators like fraction, conformable, quantum. We formulated a series of classes of analytic function generating the well-known Salagine differential operator. And these are some of recent references. I exclusive only the very recent very recent references. Thank you very much for your listen. If you have any question, I will be very happy.
Thank you, madam, for the nice presentation lecture. Participants, if you have any clarification or questions, you can ask now. Okay, if there is no questions, then we conclude the first session. As a chairperson of this session, I thank Rabha W. Ibrahim ma'am for clearly explaining the concepts in geometric functions formulated by differential operators and explaining fractional function theory, complex comfortable calculus, quantum calculus, and applications of cube functions and Bryant-Bucket differential equations and their applications in physics and mathematical biology. Thank you very much, madam.
Thank you very much. Thank you very much. Okay, thank you.
Over to Hari Krishna.
Thank you, sir. I would like to invite Dr. S. Harikrishnan, co-convener of ICCM 2K21, to propose a vote of thanks.
Thank you. Thank you very much.
I think you can inform the participants when the next lecture will start.
Okay, sir. Thank you, sir. Dear participants, we will get back by 12 o'clock for the second session of ICCM 2K21.